You know, if you really look around, light is doing some pretty strange things. I mean, it's creating illusions on hot roads, making straws look bent in a glass, and it's hiding all these secrets right in plain sight. So today, we're going to crack the code. We're going to use just a few simple rules of ray optics to solve some of the most beautiful puzzles light creates for us every single day.
All right, let's start with a puzzle I bet you've wondered about. You see a rainbow, right? This perfect, beautiful arc of color shooting across the sky. But why is it always just an arc? I mean, where's the rest of it? But here's the twist. Sometimes you can see the whole thing. People in airplanes report seeing these full, perfect circular rainbows all the time. So what's going on? What's the secret? What changes when you're thousands of feet up in the air? Well, that's the mystery we're going to solve.
Now, to get to the bottom of that whole rainbow thing, we first have to realize that it's not the only puzzle light creates, not by a long shot. Our world is absolutely filled with these incredible optical tricks. I mean, think about it. You've seen that shimmering puddle on a hot road, right? And it just vanishes as you get closer? That's a mirage. Or what about a perfectly straight straw that looks totally broken the second you put it in a glass of water? These aren't magic tricks. They're physics puzzles just waiting to be solved.
And like any good puzzle, these all have a solution. To figure it out, we need a toolkit, just a couple of essential rules that tell us how light behaves. And once you know them, all that magic starts to look a lot more like science.
And just how important are these rules? Well, let me put it this way. In some of the world's toughest physics exams, like the JEE in India, this one topic is worth over 5% of the entire score. That's how fundamental these ideas are. They're basically the bedrock for understanding how we see, well, everything. So what are these rules? It really boils down to two main behaviors. First up, we've got reflection. This is just light bouncing off a surface, like a mirror. And the rule is so simple and elegant. The angle it comes in at is the exact same angle it leaves at. Then there's refraction. This is when light passes through something and bends. This is the guy responsible for that broken-looking straw.
Now that bending, it isn't random. Nope, it follows this beautifully precise rule called Snell's law. And really, all this formula tells us is that the amount light bends depends on what it's traveling through. It's kind of like the master equation for predicting exactly how light's going to change direction, whether it's going from air to water or glass back to air.
Okay, so we've got our rules, bouncing and bending. Now let's put them to work, because this is where things start to get wild. Once you know how to bend light, you can also figure out how to trap it completely.
And a simple glass prism is the perfect laboratory for this. See, as a ray of light enters the prism, it bends. And then when it leaves on the other side, it bends again. Using a rule like Snell's law, we can predict its exact path, from the very beginning to the very end.
So how would you actually solve this? It's a really cool step-by-step process. All we need to know is two things: the angle of the prism itself and a number called the refractive index, which basically tells us how bendy that specific type of glass is for light. You plug those two things into a simple formula, and it tells you the exact angle the light will be deflected. The rules just work. It's perfect.
But what if you bend the light so much that it can't escape? This leads to an amazing phenomenon called total internal reflection. Imagine this. You're underwater, and you're shining a flashlight up at the surface. If you aim it at a steep enough angle past this tipping point called the critical angle, the light actually fails to get out. The surface of the water suddenly acts like a perfect mirror, reflecting all the light back down. This is actually the principle that makes fiber optic cables work.
And this right here, this shows that tipping point perfectly. The ray of light hits the boundary at exactly the critical angle, see, and it just skims right along the surface. Go at an angle any less than that, it escapes. Any more, and it's trapped. And if you thought that was cool, get this. This whole trapping effect is color dependent. Yeah, it turns out the critical angle is slightly different for each color of light. It's bigger for red, smaller for blue. What does that mean? It means you can set up a situation where at one specific angle, yellow light just skims the surface, blue light gets totally trapped and reflected back, and red light escapes completely. You can literally filter light and separate colors using nothing but physics.
And total internal reflection isn't just some neat lab trick. It happens on a planetary scale. The way that long-range radio waves bounce off the ionosphere to travel all the way around the globe, that is the exact same principle as light reflecting off a layer of hot air to create a desert mirage. We're talking two vastly different scales, but one shared, beautiful principle.
So, we can bend light and we can trap light.
What happens when we start to shape materials to control that bending with real precision? Well, we get lenses, our tools for literally shaping reality.
And lenses are all about predictable control. Take a simple plano-convex lens, one flat side, one curved side. It actually doesn't matter which way you turn it. The physics of how light bends through those curves means that it will always bring light rays together, acting as what we call a converging lens.
But the images these lenses create can do some really weird things. For instance, get this. If you move an object towards a lens at a perfectly constant, steady speed, its image doesn't just move away smoothly. Instead, the image accelerates away, speeding up faster and faster as it flies off toward infinity. It's this strange, nonlinear dance, all dictated by the laws of optics.
All right, our toolkit is officially complete. We've got reflection, we've got refraction, and we know how different colors can be bent or even trapped. We are finally ready to go back and solve the mystery we started with, the secret of the rainbow.
So here's the big secret. A rainbow isn't a thing. It's not an object that's just hanging out there in the sky. It's an optical effect that exists only for your eyes at a very specific angle between you, the sun, and the raindrops. Every single raindrop acts like a tiny prism, creating a full circle of color. You just have to be in the right place to see it.
So why do we only see an arc from the ground? The reason is so simple. You're going to love it. The Earth gets in the way. That's it. The horizon just cuts off the bottom half of the circle. But when you're way up high in an airplane, there's no ground blocking your view of the raindrops below you. And so you can finally see what was there all along, the primary and secondary rainbows as complete concentric rings. Puzzle solved.
So what's the big takeaway from all this? Well, once you get a handle on these fundamental rules, you don't just see the world anymore. You start to understand it on a whole new level.
The very same principles are at play in so many things. The way a mirror works, the reason a lens can focus light, what causes a desert mirage, and the secret behind a full-circle rainbow, it all just comes back to light bouncing, bending, and sometimes getting trapped.
So I'll leave you with a little challenge. Now that you have this toolkit, what else can you explain? The next time you see light shimmering on the surface of a swimming pool, or you see a reflection in a curved window, don't just see the illusion. See the physics. See the elegant rules of light playing out right there in front of you.